In this video, I want to go through a test bench I wrote to test that FIFO buffer. You can read this on your own. It's really not that difficult. I'll just go quickly through it, not in details. You can see that I basically defined some local parameters, and I put these parameters as data width and address width here, so I can change them right away if I choose to. And of course, that depends on the clock period like we've seen before. And I just instantiated a version of that FIFO, and again, I just basically generated a clock, generated some reset signal for half a clock cycles at the very beginning. I made sure that my read and write initially are basically 0. I didn't have to, but I just basically put that. And then I generated a bunch of test vectors, and these test vectors, you're going to see there's a lot of them, but you can read them there. They basically, I tried to follow the exact graphs you've seen in the circular implementation. So if you can see it in here, I decided that the data width should be 8, and I have address width is 3. That means I also have 8 locations. Okay, so, and you can see that basically I'm reading and writing and making sure that it's empty and full and whatnot. So let's go through this test bench in here and read it. What I will do is I'll clean it up a little bit so that we get to see some useful information. So these are just the parameters. I usually don't it's like we don't change them. These are the parameters. So I'm going to just highlight all of them and delete it. Now I have everything I need, but sometimes you might want to do something else, like with the, I believe if you go to the object in here with the scope and you clicked on that, so the unit under test, you're going to see that this is the R file unit. Is basically the memory unit, basically the register. So you can see in here, I don't see the content of the memory, the linear content of the memory. You will see that I have a clock, I have a reset, the read and write signal, and whatever I put in the input, whatever I put in the output. And of course the full and the empty signals like an end user would. So an end user would not know the internals of the FIFO. It just can see whatever you put on its input, whatever you put on its output. But we're designers, so we should get access to the internal memory. However, the internal memory is an internal, you can see, if you remember the FIFO, let me just show you. The FIFO has inside it the register file in the controller. So this is actually living within the register file. So if you click on the register file, you get the internal signals, including memory, the one that we decided here. So if you actually click on the register file, you can see that we have memory. So what I'm doing right now is I'm actually going in here and I'm just basically drag this guy in here and you get to see the content of the memory. You're not going to see it right now because what you need to do is you need to save this simulation here. Okay, you can save that simulation. I just basically hit the control and save, and now you can run that simulation again, and you can see it'll actually it will just show you the same exact graph with the content of the memory available to you if you choose to. So here's the simulation after it ran, and again now I get access to all of the memory, and you can see that it has a bunch of excess because the memory initially is empty and then I fill it, like I fill it till I get in here, and this is basically when it gets full. But anyway, if you wanted to, you can actually track the memory in here. And for now, I'm not going to just tell you what's the content of the memory, but you can actually follow it. It's not really difficult. What I want to do is I want to show you what's happening in here. You can see initially I do have an empty FIFO. This is why the empty is actually high. And of course, what's happening in here is the following. I'm basically just resetting for half a clock cycle just to make sure everything is fine. And then I'm setting basically the input to be 5, and I'm issuing a write signal in here. So with the write signal, again, what we have is we have a first word fall through. So I don't have to issue any read signal. You're going to see that this 5 will directly go, like, remember it's active at the positive edge of the clock. So at the positive edge, I'm going to see that the 5 I put at the input is directly out, like it just fell directly to the output, and my R data is my output, my write data is my input. Okay, and then I can issue a bunch of other write signals. You can see I'm writing an 8, I'm writing a 2, and then, but the output is still at the 5 because it's a FIFO buffer. It only reads whatever it's at its head, and the head was 5, and I didn't issue any read command. So if you issue a read command, as you can expect in the next clock cycle, you can see that it will basically drop that 5 and read the next 8, or actually show me the next 8, and that's what happened in here. Good. Now what I'm going to do is I'm going to issue a bunch of write commands. So you're going to see a write command in here. I'm writing a 0, I'm writing a 9, I'm writing a 3, I'm writing a 6, I'm writing a 1. What I'm trying to do here, I'm trying to fill it. In my test code, you're going to see that I basically wrote, let's see this. I wrote 1, 2, and 3, and then I went and read 1. So basically I have 2 locations that are full, and then I have 3, 4, 5, 6, 7, and 8. And basically at this particular point, when the positive edge of the clock comes in, you can see that the full signal got raised, and now I know it's a full buffer. So if I'm actually to write anything in here, nothing will be written because I should check if the buffer is full or not. Next, what I'm going to do is I'm going to just read. So you can see that here, the negative edge here, what I did is I issued a read. So at the positive edge, you're going to see that the read signal that we will be reading is the one that is right after the 8. So we know that 8 is in here. So it's going to read the 2. And that's what happened. So the output is now 2. I changed the input to 3, but nothing. This 3 is not going to be inputted or stored. So after the 1, I put basically the signal to be, let me just see. In here, I actually wrote it. Yes, it's written. So the last value is written. After the 1, you're going to see a 3. It's written, definitely. And that's basically the last value in it. But anyway, we go back in here. You can see that I'm reading a 2. I issue another read. It's reading the 0. And then I expect to see the 9, the 3. And what I'm effectively doing is I'm actually trying to empty the empty the buffer. That 3 is different than the last one. It's actually this 3 in here. And then you can see a 6 and then a 1. And then that's the last 3. And of course, as we expected, that's the last 3, and I'm actually issuing the last command in here, and it's reading. It's basically telling me it's empty, and it moved to the next location. Okay, and the next location now it's basically empty. I know that this particular location here is junk. There's nothing in it that is useful. I'm reading an empty. Like if you're reading the data, the 0.8 is actually junk. But if you think about it, it's really not junk. It's actually rotated back to the original 0.8 in here. But because I know that it's empty, this particular value is not valid because the buffer is empty. But the point in here is 8 has not been overwritten, but it's indicated that this 8 is available for the next value to be written to. And now what I want to do is I want to test, here you can see that I basically tested the read and the write. I tested whether it's full or empty and what's happening, and everything is working. Now what I want to do is I'm testing whether if I'm actually reading and writing at the same time. Of course, the buffer is empty. It's exactly at the same time, at the same location as at the very beginning. There's nothing in it. Well, technically, if you take a look at the memory, you can see that there are certain values stored in memory, but all of them are not valid because I read them already, so I can overwrite them. So what I'm going to do now is I will test my code, and my code in here, I'm going to issue a read and write command, and what I'm putting at the input is 7, and you can see at the negative positive edge, okay, that 7 got written to the memory and it fell directly to the output. And this is the code where we dealt with the 1-1 case, and when I told you do not move the read and write pointer, and you can see now if you kept issuing these read and write pointers, you're going to see that the 7 will go out, the 8 will go out, like whatever you put, it's basically in here, and it's still empty. Okay, it's still empty. So you put a 7, and that 7 basically fell through, and it's available at the output. But technically, a system should know that the FIFO is empty, so this value is not valid anymore. If you read it once, and that's about it. Next, we are going to do a write command in here, or actually a read command, but it's an empty buffer. So technically, nothing should happen in here, and I'm not moving it because I'm basically, if you go to the controller and we go to the read buffer in here, it's basically an empty one. So basically, I'm testing, is it empty? Yes, nothing will happen. So I'm just keeping everything there. Technically, you're not supposed to read because I know it's garbage. Basically, this data is not necessarily valid. Now, what I'm going to do in here is I'm going to write a few data points in here. I'm going to write a 4, I'm going to write a 5, I'm going to write a 6. Okay, the output is still 7, okay, all the way through, but wait a minute, let's talk about the 4 in here. So what happened with the 4 is the buffer is empty, and it was at 7, and we said that 7, even though that I wrote it and it just directly went to the output, you can see that what happened with this particular 4, it actually fell through, and now it's the first available word, and it's actually going to be available in the output, and this is actually a valid output, basically, because I'm not reading, I didn't issue a read command. Okay, you can see now I'm writing a 5, I'm writing a 6, but the 4 is still there. The point I'm trying to make in here is I basically wrote and read 7, so I stored in that location 7 and I made it available. The next time I read it, it just ignored it, but that 7 is still stored. And then what I did is I wrote something. So what happens is like this particular 7, because the buffer is empty, it got overwritten right away, and we wrote a 4. And because we're dealing with a fall through, directly fall, like first word fall through FIFO buffer, so that 0.4 got to the output directly in here. Okay, good. So that's good in here. So let's you can see basically I'm doing a write in here and another write in here and another write in here, and I issued another read and write while it's not empty. And you can see what happened is I was at the 4, it read the next point, And also, it would have written after the 6, it would have written the 7. So it's actually moving the pointers away. And you can see this particular 7 in here. It should be written somewhere. So you can see it. It's in the 7. That's why you can see in here 7 is not necessarily the last row in the memory. This is, you can think about it as the linear version of it, which is 0. I have a 3, a 4, and a 5, and a 6, and a 7. This is why we deal with the pointers and the circular implementation.